MBA 633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we will see the mechanics of doing hypothesis testing of the population mean when the population standard deviation is known or sigma is known. So consider the following problem. An insurance company is reviewing its current policy rates, and when the rates were originally set, they believed that the average claim was $1,800. And now they're concerned that the true mean is actually crept up higher, and if it has, they may end up losing a lot of money. So they randomly selected 40 claims and calculated a sample mean of $1,950. So as a result of this testing, the question being asked is, should the company be concerned? And notice that the problem says that we should assume that the standard deviation of all claims is $500. In other words, the sigma, the standard deviation of the population, is given to us as $500. So you can see that the population that we are dealing with here is the set of all claims that the company faces, and the population parameter of interest here is the average of all these claims. Now we have a claim and a counterclaim. If we want to see whether the company should be concerned or not that the average claim has gone up, we are setting up a claim and a counterclaim about the population parameter. Now notice how these two have been set up. Your initial inclination might be to set up what we are trying to establish, namely a suspicion that the mean has gone up beyond 1800. Your initial inclination might be to set this up as the claim. In other words, set this up as the null hypothesis. So you might initially be inclined to say, oh, H0 is mu greater than 1800 because that's the claim we want to establish. However, that would be a mistake simply because of the way we do hypothesis testing. If you recall from our introductory segment on hypothesis testing, the way we do it is, given that we can't do any kind of inferencing with absolute certainty, the way we do hypothesis testing is to minimize the likelihood of a type 1 error. What that means is we do our hypothesis testing in a way that we have a very low likelihood of rejecting the null when in fact it's true. So we would like to set up our null and alternate hypothesis in such a manner that whatever claim it is that we are trying to establish, or whatever suspicion it is that we are trying to confirm, that we would prefer that to be the result of a rejection, because we know that when we reject the null, we have a fairly low likelihood of having made a mistake. Therefore, that is the reason why this suspicion that we are trying to confirm, that the mean average claim might have gone above 1800, that's why it has been set up as the alternate. Now it will take some practice, as I mentioned, to set up the null and the alternate, and this is perhaps the most difficult step in hypothesis testing. The rest is fairly mechanical, a bit tedious perhaps, but quite mechanical. So the null and the alternate hypothesis that we have here is mu less than or equal to 1800, and the alternate is mu greater than 1800. So where do we go next from here? Notice that the problem tells us that we are to use an alpha of 0.05, or a level of significance of 0.05. The physical interpretation of that being, I'm willing to accept a 5% chance of making a type 1 error. Since I cannot do the inferencing with absolute certainty, that's the level of uncertainty I'm willing to accept of making a type 1 error, rejecting the null when in fact it's true. So what do we do next? Our next step, of course, is to look at what the sample is telling us. So we start off with the assumption that the null is true as an equality. So all hypothesis testing stems from the assumption that the null is true as an equality. So if that's the case, then mu is 1800. Okay, and the null is true as an equality, and here we have the sampling distribution of the sample mean. So we know that if mu is in fact equal to 1800, I know that x bar, the sample mean, will be normally distributed with a mean of 1800 and a standard deviation. You'll have to excuse this little flashing back and forth. My machine is old, and it tends to slow down when there's so many processes are going on at the same time. So the standard deviation of the sample mean here would be 500, which is the population standard deviation, divided by the square root of the sample size, which is 40. and this of course would be in dollars. Okay, and we are observing a sample mean of $1,950. So obviously what we are seeing in the sample is suggesting, this 1950 is suggesting that it looks like HA is what we should go for. In other words, 1950, the sample statistic, is suggesting that we should reject the null. But of course we have to quantify, because this 1950 could have come about purely by chance, even though the true population mean might have been $1,800. It's possible that to still get a sample mean of 1950. The question is, how likely is it to happen by chance? And if we end up computing that it's very, very unlikely to get a sample mean of 1950 or higher, if the true mean were in fact equal to $1,800, then of course we would feel more comfortable in rejecting the null. So let's see, the usual process of deciding whether a value is really extreme or not is simply to standardize it. So here we have our z-score. This is our standardizing. So the sample statistic is 1950. Is it really extreme? So what do? I subtract it from 1800, which is the presumed mean, and divide it by the standard deviation of the sample mean, which is simply 500 by square root of 40. So let's see where that gets us in terms of a value. So 1950 minus 1800, that's the numerator, and the denominator is equal to 500 divided by square root of 40, and you divide one by the other. 1.897. So what we are seeing here is that the sample statistic that we got, the $1,950, is 1.89 standard deviations to the right of the center. Okay, so how likely is it to get at least that extreme a value? So the likelihood, the probability of x bar being greater than 1950 is equal to equal to 1 minus norm dist of 1950 comma 1800 comma standard deviation is 79.05 comma 1. So that is equal to 2.8%. Okay, so the physical interpretation here, and this is what's called the p-value. Okay, so the physical interpretation of the p-value is, it is the probability of getting a sample statistic at least as extreme as the one we got if the null were true as an equality. And notice, why did we compute the right hand tail over here as in terms of the probability? Simply because our alternate hypothesis is a right-sided hypothesis. We are saying mu is greater than 1800, so we are computing the right side tail. So what we are saying here is, if the true sample mean, I mean the population mean, the average of the claims that this company received was in fact $1,800, then there is only a 2.8% chance that I would have seen a sample statistic of $1,950 or more. Highly, highly, highly unlikely. And notice, I am willing to accept a 5% chance of making the wrong call, or 5% chance of making a type 1 error. Since 2.8% is less than 5%, in other words, p value is less than alpha, then this probability is less than the level of uncertainty I'm willing to accept in terms of making the call. So the final call that I will make is that I will reject the null. I will reject H0, simply because the likelihood of seeing a sample statistic as extreme as the one I got, if the null were true, is very, very low. It's lower than my threshold of uncertainty that I'm willing to accept. So I feel comfortable in rejecting the null. So I end up saying, yes, I think the company should be concerned because it's very likely that the average claim has gone up beyond 1800. Notice that this whole exercise tells me absolutely nothing about how much it has gone above 1800. It simply tells me that the data seem to indicate, the sample data seem to indicate that there is a very high likelihood of the population mean, the average claim amount, having gone above $1,800. So the method that we just used here is what is called the p-value method. So we computed the probability of seeing at least as extreme a value, at least as extreme a sample statistic as the one we got, provided the null is true as an equality, and then we compared that with alpha. There is another method, a complementary method, if you will, of going about doing the hypothesis testing. That is called the critical value method, and maybe in the next problem that we solve, we will use that. And both should give you the same result. So the end result of the exercise here is that we would reject the null hypothesis and conclude that yes, the company, the insurance company should be concerned. The sample data appear to indicate that the average claim amount, the population mean, has gone above $1,800.